Hello everyone, I welcome you all again to the lectures of electromagnetic induction. I am Samir Lavankar. This is lecture 5 part 1. So, let us go. So, moving to the course outline again, we have already covered electromagnetic induction's introduction, what is electromagnetic induction, definition of electromagnetic induction, followed by the experiments of Faraday and Henry. There were 3 experiments, followed by magnetic flux denoted by phi b. Moving on to the Faraday's law of induction, that is epsilon value, the voltage value which we calculated was Faraday's law of induction. Moving on to the Lenz's law and conservation of energy, that is how negative sign comes into picture in Faraday's law of induction's mathematical term. Moving to the motional electromotive force, as in that only and only constant magnetic field is not responsible for generation of electromagnetic induction, even moving of conductor can also induce current. And now we are in the last lecture I started inductance of mutual inductance. So, let us move on to the future discussions of inductance only. Just a quick recap, in the last lecture we learnt about this figure here on your right. It has 2 coaxial solenoids of each length L, and then finally the mutual inductance was being calculated as M12 is equal to mu N1 N2 pi R1 square into L. It has to be implied here that L should be greater than R2, that is L is very long in when it is compared with the radius. What is R2 here? Just to iterate you again, R2 is this, the radius of the bigger solenoid. So, now let us again conclude or further let us discuss further. So, now please just listen here, that let us reverse the case now. What is reversing the case here? In the last lecture what we did was we found out the mutual inductance. I will iterate here from here, that we found out the value of M12. What is M12? M12 is the mutual inductance of solenoid S1 with respect to solenoid S2. So, now we will reverse and see if the mutual inductance value will change or it will be same. This is the discussion we need to carry out in this lecture here. So, now let us consider the reverse case. So, a current I1 is passed through the solenoid S1, this is solenoid S1 here for your reference, and current I1 is passed. So, any current which passes through S1 we are denoting it by same sign only. So, current I1 is passing into it, unit is ampere, and the flux linkage, please remember flux linkage is nothing but N into phi. So, if we are talking about the flux linkage in second solenoid, it will be N2 phi 2. If we are talking about the flux linkage in solenoid S1, then it will be again N phi N1 phi 1. Please make sure of this concept, very small concept but very important concept. So, now current I1 is passed through solenoid S1 and the flux linkage with coil S2 is N2 phi 2. In the last lecture also we found out similar equation only, in which we found out N1 phi 1 is equal to Mi, some M is denoted with 1 2 and 2 here. Just reversing the case, we will get N2 phi 2 is equal to M21 I1. Please make sure this time it is not M12, it is not M12, it is M21. So, this is a little difference from the last case. Now, what is M21 here? M21 is the mutual inductance of solenoid S2 with respect to S1. So, how to remember the stuff here, that what should be the denotation of the mutual inductance? The number which you are writing towards the right is with respect. So, this is for with respect to which we are talking about, and this is the solenoid which is in picture. So, it is the mutual inductance of solenoid S2 with respect to solenoid S1, with respect to solenoid S1. So, this is a small concept again. Moving on. The flux due to the current I1 in S1 can be assumed to be confined solely inside S1. So, it is so for sure only that if this is the solenoid we are talking about, if this is the solenoid we are talking about, the current I1 is restricted into this portion only. Hence, the flux due to current I1 in S1 can be assumed to be confined solely inside S1. So, the flux value is also confined in this area only. Since the solenoids are very long, So, as the condition or the assumption is that L is very much greater than R, that is why this is here this assumption is true here, that the flux due to current I1 in S1 can be assumed to be confined solely inside S1. This is please make sure that this is also an assumption here. This is also an assumption here. Since the solenoids are very long, thus flux linkage with solenoid S2 is, what is flux linkage? Just iterating it again, flux linkage is nothing but N into phi, because we are talking about the solenoid S2 here, so it is N2 phi 2. Moving on. So, the flux linkage is directly N2 phi 2 is equal to N2L. What is N2L? N2, in the last lecture I told you that N2, small n2 is nothing but number of turns in that particular coil per unit length. So, just it rearranging, we get N2 is capital N2 is equal to small n2 multiplied by L, which is written here. Phi is nothing but, from this formula also, it is B into A. So, it is pi R1 square, because we are talking about the flux is only and only available where? Inside S1. That is why the area of S1 has to be taken into picture. So, it is pi R1 square into mu naught N1 L1. This same concept has been already iterated in the last lecture. So, N2 phi 2 is equal to small n2L into pi R1 square into mu naught N1 I1, where N2L is the total number of turns of S2 as depicted here. Moving on, thus M21. So, now just using this equation and using this equation, we get M21 is equal to mu naught N1 into pi R1 square L. Remember this, and let us move on to the first case. If you see, the formula is same here. That means it does not depend that the mutual inductance we are talking about depends on any case or depends on any solenoid. If the solenoid is reversed, or if the current passing through any solenoid is reversed, let us say we are talking about the current passing through I1 coil, S1 coil, or we are talking about the current passing through second coil, the mutual inductance remains same. It remains same. So, M21 is equal to mu naught N1 into pi R1 square L. Hence, it is also written here that M21 is equal to M12 is equal to M. So, this is the concept we got when we calculated both the cases. So, let us move on. We explained the above example with air as the medium. So, please make sure air as the medium, as in anything which is not coil is air. So, air is present here, air is present here. So, air is the medium we are talking about here. So, when air is the medium, so this is again an assumption here that everything surrounding the solenoid is the air. So, we explained the above example with air as the medium within the solenoids. Instead, if a medium of relative permeability mu r had been present, the mutual inductance would be just a simple multiplication of the previous formula is multiplied with mu r here. What is mu r? Mu r is medium of relative permeability, denoted by mu r. Moving on, it is also important to note that the mutual inductance of a pair of coils, solenoids, etc. depends on their separation as well as their relative orientation. What does relative orientation mean here? Let us say, for example, in this case we took a simple case in which both the solenoids were coaxial. Coaxial means both have the same axis, but it does not have the orientation same every time. It can be like this, that the small R1 solenoid is like this, but the bigger is a little tilted. So, the mutual inductance will change. What may change? The value of theta may change. What may change? The value of B may change. What may change? The value of area, the projection of area may change. Anything can change. So, this is the only concept being talked in the last point. Iterating again. So, it is also important to know that the mutual inductance of a pair of coils, solenoids, etc. depends on their separation as well as their relative orientation. Separation as in the value of radius if the radius change, if the value is coaxial here, if the value is coaxial, if the radius of small solenoid is this much, big solenoid is this much, or else if the solenoid is kept, one solenoid is kept here, one solenoid is kept here. So this is the relative separation talked about here. So all in all, mutual inductance is nothing but for two solenoids kept coaxial, it is M21 is equal to mu naught N1 into pi R1 square L. So let us move on to the problem, one of the problem associated with mutual inductance. So please iterate here, please listen carefully, what is the problem talking about. So two concentric circular coils. So two concentric means having the same center. If the center of any two circles have the same center, then those two circles are called as concentric circular coils. So it is circular, these are circular coils, and coil as in anything round upon anything which is wound upon a conductor of electricity such as iron nail etc., passing through a battery, and itself the wire wound up should be a conductor of electricity, but it should be wound by an insulator. So that thing is called as a coil. Simple iterating stuffs which I already talked about in the previous lectures. Moving on, so two concentric circular coils, one of small radius r1, one has a radius r1 and other of large radius r2. So it is evident that r2 is greater than r1, such that r1 is less than r2. So it means this is the concept being talked here, that r2 is very much greater than r2, that is the separation between the two coils is very large, are placed coaxially. Coaxially means if both the coils have the same axis. Coaxially is nothing but same axis. If the axis is same with centers coinciding is nothing but concentric only. So are placed coaxially with centers coinciding, then obtain the mutual inductance of the arrangement. So the formula is also updated here for a quick reference. I keep on adding the formulas here. So new formula has been added, that M21 is equal to M21 or M12 is equal to mu r is the coefficient of relative permeability, mu r is equal to M21 is equal to mu r into mu naught into N1 into N2 into pi R1 square L. So obtain the mutual inductance of the arrangement. So please look to the solution here now. So let a current I2 flow through the outer circular coil. So if I iterate the concept again, so let this be bigger coil with radius r2, let this be smaller coil, let me make it much bigger because it is given here that r1 is very less. So let us say this has the radius r2 and this small one has the radius r1. So now it is said that the current is flowing in this coil. Let us say the current is I2 here. So let a current I2 flow through the outer circular coil. The field at the center of the coil is this is the center of the coil. So this is the center of the coil. So B2 is equal to mu naught I2 upon 2R2. This is nothing but the concept we talked about in the last lecture when we were deriving the concept of magnetic induction, mutual inductance, not magnetic induction, mutual inductance. So now B2 is equal to mu naught I2 upon 2R2. Since the other coaxially placed coil has a very small radius, that is R1 is very small than R2, B2 may be considered constant over its cross sectional area. So this is the assumption being put here. Now therefore phi 1 is nothing but B dot A. So B dot A area is given here as pi R1 square into B, and then finally only positions are put here. So pi R1 square is same, value of this has been put into this equation here. So it is mu naught pi R1 square upon 2R2 into I2, and this is nothing but M12 into I2. As we already know, for coaxially coils, M12 is equal to M21, which is equal to mu naught pi R1 square upon 2 R2. Hence, this is the answer here in front of you, that the mutual inductance of the arrangement is nothing but mu naught pi R1 square upon 2 R2. Moving on, little note on this concept, little note on this problem here, little note on the complete discussion here, that we calculated M12 from an approximate value of phi 1. Approximate value of phi 1 was being used here, assuming that the magnetic field B2 to be uniform over the area pi R1 square, because the value of R1 is very small. So, the change in the magnetic field with the space is very less. dB by ds, if I write space as ds, is approximately equal to 0. That means the value of B here almost in this region is same. It is varying very less. So, that is why we took this assumption, and hence we calculated the value of phi value with a constant value of B, assuming that the magnetic field B2 to be uniform over the area pi R1 square. However, we can accept this value because R1 is less than R2. Because of this assumption being written in the question, we calculated the value of B with a constant magnetic with a constant value. Moving on, so a little more discussion has to be done, but that will be considered in the next lecture. So, in this lecture what we studied about is, we studied the reverse case of mutual inductance, and we found out that the value of M12 is equal to M21 is equal to mu naught N1 N2 pi R1 square L. If the value of air as a medium is being kept, then the value is multiplied by 1, but if another medium is being used, then the coefficient of relative permeability, that is mu r, has to be multiplied with mutual inductance. A simple concept, a simple problem in which R1 was very less than R2 was being used, so as to apply the concept, or so as to apply more assumption that a constant magnetic field is also required in some instances, and future discussions of future problems will be dealt in the subsequent lectures. So, for this lecture, this is the course progress for us. We have completed introduction, experiments of Faraday and Henry, magnetic flux, Faraday's law of induction, Lenz's law and conservation of energy, motional electromotive force. We are talking about mutual inductance in the concept of inductance here, and after mutual inductance I will teach you the concept of self inductance, followed by AC generators, and that is the end of electromagnetic induction. So, for now, thank you.